On September 15th, 2017, in an epochal sacrifice worthy of a god, one of humanity's greatest feats of exploration finally came to an end. In a glorious death spiral, after executing 22 swan-like arcs around the planet Saturn, and making the first ever observations of the region within the planet's rings, a spacecraft turned its eye toward the swirling storms below and plunged into the planet's upper atmosphere, igniting into a meteor and merging with the seething clouds. Intended as the follow-up to the hamstrung Galileo mission, the Cassini mission to Saturn would so far surpass it that for 13 years it effectively became an outpost for our civilization, making the most distant of the ancient planets as familiar to us as our own, and providing images comparable to the greatest art. Cassini was launched in 1997, when Galileo was just completing its primary mission around Jupiter. Arriving in Saturnian orbit in 2004, it proceeded to image the planet's dizzying gallery of moons, rings, and shrouded storms in unprecedented detail. Cassini was not the longest of NASA's planetary orbit missions. Indeed, the Mars Odyssey orbiter has been circling its planet since 2001. But it was, perhaps, the most expanding, revealing landscapes both utterly alien and shockingly familiar, all never seen before, and all forged primarily of water. One of these water worlds in particular had seized the imagination of Cassini's crew before the probe had even been launched. Cassini was named after Giovanni Domenico Cassini, an Italian astronomer who lived during the 17th and early 18th centuries. A younger contemporary of Galileo, he would follow in the great man's footsteps, not only by discovering 4 new moons of a distant planet, but also by naming them after his patron, in his case, King Louis XIV of France. These Louisian stars, or Sidera Lodoicea, would eventually be named Iapetus, Rhea, Tethys, and Dione. He was also the first to discover that Saturn's ring was not a homogeneous structure, but appeared divided by a wide gap, now called the Cassini division. Somewhat ironically, given that we now know that Saturn's rings are riddled with gaps and grooves, we also know that the Cassini division is not one of them, but is in fact a band of dark material. Despite his name attaining the glory of a NASA mission, in truth, Cassini was something of an also-ran in the story of the exploration of Saturn. While he may have enriched our understanding of the complexities of the Saturnian system, he was not the one to first crack open the 6th planet and reveal its mysteries. The namesake of the man who was tucked snugly into the spacecraft's side, awaiting its soft release and final descent into the frigid atmosphere of one of the strangest worlds in the solar system. The hardy little probe was named Huygens. Huygens?
Excuse me, I think I may be able to help here.
Oh, hi, friend Mythic. He's a friend from another channel.
That's right. On my channel I talk about life on other planets, alternate history and other interesting stuff.
Yep, love your illustrations, by the way. Seriously, guys, check them out. They're really cute. But, why do you think you can help me here?
Well, I am myself of Dutch origin, and I heard you were struggling with the pronunciation there.
Ah, yes. Dutch pronunciation. A stumbling block for even the best-intentioned English speakers. I'd certainly be grateful for any advice.
Awesome. Okay, so the first tricky part is the diphthong UI in modern spelling or UY in archaic spelling. It sounds like this. Ui. Ui.
Ui. Ui.
The next stumble block is the letter G, pronounced as g, which you may know in English from Scottish loch, although generally more raspy. So, huygens.
Huygens.
Yeah, that will do. I'm sorry, the Dutch language is a bit special. Now I don't want to keep you from your fascinating video, so please do carry on. Love your channel, by the way.
Ditto, and looking forward to your next video. So, what Galileo Galilei was to Jupiter, Christian Huygens was to Saturn. The first to peer at that indistinct star and begin to prize out its individual personality and oddments. In particular, he was the first to identify that Saturn had a ring. Huygens was born in 1629 to one of the most distinguished families in the Netherlands. As befits a man of the Renaissance, he was a mathematical and engineering prodigy, By the age of 23, he was already manufacturing the most powerful telescopes of his time, with up to 43 times magnification, more than double that used by Galileo. By the age of 27, he had invented and patented the pendulum clock. Yes, the same pendulum clock in your grandparents' hallway, which would remain the gold standard for precision timekeeping until the invention of the quartz oscillator in 1927. Huygens was a prodigious academic and writer as well. The same year he patented his clock, he published his first treatise, a refutation of Descartes' speculations on elastic collisions. As a writer, he aimed to popularize astronomy for the general public. His musings on the possibility of extraterrestrial life call to mind those of Carl Sagan 300 years later. A man that is of Copernicus's opinion that this earth of ours is a planet, carried round and enlightened by the sun, cannot but sometimes have a fancy that it's not improbable that the rest of the planets have their dress and furniture, nay, and their inhabitants too, as well as this earth of ours." Unquote. Galileo had shown that the moon and sun were not ethereal, mystical objects, but perishable, terrestrial worlds just like our own. If that were the case, should they not also have life? For all that, it is for a series of discoveries made with his groundbreaking telescope in 1655, at the age of 26, for which Huygens is best remembered. In March of that year, alongside the aforesaid ring discovery, Huygens became the first person since Galileo to find a moon around another planet. Unlike Galileo, he failed to find more than one, and so simply referred to it as, quote, Saturni Luna, or Saturn's moon. Even Cassini would neglect to name his own crop of moons. It would not be until 1847, a year after the discovery of the last planet, Neptune, that renowned astronomer John Herschel would establish the convention that Saturn's moons be named for the Titans, the deposed family of Kronos, the Greek Saturn. The 6 smaller of Saturn's then-known moons were named after specific Titans or Titanesses, while Huygens' moon, the largest, was named simply Titan. Evidence prior to the voyagers suggested that water was the prime material of the Saturnian system, though water frozen to temperatures approaching absolute zero. But what would these rocky snowballs actually be like? Dynamic, active worlds like our own? Or inert, undifferentiated lumps? When the voyagers at last reached Saturn in the early 1980s, the retinue of snow-white pearls they revealed not only showed that the Saturn system was geologically alive, but that ice, like rock on Earth, is the material out of which these geological forces shaped and sculpted their surfaces into myriad landscapes. At Saturn's distance from the Sun, ice effectively petrifies, adopting the properties of rock, allowing it to display many of the features that on our world would be forged from granite or basalt. The moons of Saturn were revealed to be riven by tectonic fractures like the rift valleys of our world, broken by upwelling plumes of magma composed of liquid water. They showed regions devoid of craters, indicating that their surfaces had been covered over with fresh material from below. The idea that cryovolcanism, or volcanism in which liquid water plays the role of lava, was present in the Saturnian system was suspected prior to the voyagers' arrival, though, frustratingly, no evidence of active volcanism was observed. It would finally be observed by Voyager 2 on Neptune's moon Triton in 1989, though Neptune's realm lies so far from the Sun's light that the eruptions were not of water, but of nitrogen. But there was one part of the Saturnian system the Voyager team prioritized above all else, so much that they sacrificed one of their probes to study it. Both Voyagers visited Jupiter and Saturn, but only Voyager 2 would go on to Uranus and Neptune. Upon reaching Saturn, Voyager 1 was shunted off the main line and redirected to its final stop, Titan. Titan is far and away the largest moon of Saturn, one of 2 moons in the solar system larger than the planet Mercury. The other is Jupiter's moon Ganymede. But while Jupiter has its 4 giant moons and little else, the material in orbit around Jupiter, excluding the Galileans, would together comprise a not very large asteroid, Saturn has 1 giant moon and a swarm of tiny worlds accompanying it. But that 1 giant moon is truly exceptional. As I'm sure you've noticed from the images so far, Titan is the only moon in the solar system with a substantial atmosphere. How Titan, a world with a surface gravity comparable to our own airless moon, could have an atmosphere is still not fully understood, though one reason is certainly its location. At Titan's distance from the Sun, not only do the frigid temperatures keep gases calm and sluggish, but the solar wind, the bane of the atmosphere of Mars, is relatively weak, lessening the effect of events such as coronal mass ejections. The presence of an atmosphere around Titan was first observed by Dutch-American planetary astronomer Gerard Kuiper in 1944, when he detected methane in the Moon's spectrum. And yes, he was an American citizen by that point, so that's probably how he pronounced his name. But the precise nature of that atmosphere was unknown. Some models predicted that methane would comprise 90% of the atmosphere, and that its surface pressure would not exceed 20 millibars, or about 2% of Earth's. Others suggested that nitrogen could form a substantial part of the atmosphere, and that it could be up to 20 times thicker than Earth. Were that the case, the greenhouse effect could warm the surface to a near-Earth-like 200 K, or minus 73 degrees Celsius. Surprisingly, media depictions of Titan in the years prior to the arrival of the Voyagers tended to be rather conservative, falling in line with the thin atmospheric model. It was the scientists who were aiming for the truly exotic. Certain atmospheric models for Titan produced a surface temperature of 94 K, or minus 179 degrees Celsius, which happens to be very close to the triple point of methane, the same gas found in Titan's atmosphere. A substance's triple point is that at which it is capable of existing as either a solid, liquid, or gas. Earth's surface temperature happens to be very close to the triple point of water, a fact not coincidental with the development of life. On Earth, water flows across the surface as a liquid, rises into the air as gas, falls as rain, and then is frozen solid as ice. This water cycle is the foundation for all life on land, sustaining and nourishing both plants and animals. To those excited astronomers, it was immediately apparent that Titan may possess an alien, frigid analog of Earth's water cycle, in which liquid methane falls from clouds and collects in lakes or seas. But that was only one aspect that made Titan so enticing. Spectrography had already shown that methane interacting with sunlight had produced a number of complex organic molecules in the atmosphere, such as acetylene or ethylene. This made Titan a curious analog to the early Earth, where similar basic carbon chemistry likely led to the origin of life. These possibilities made Titan an irresistible prospect for the Voyager team, so much that to reach it they condemned one of their craft to expulsion into the interstellar void. But the team were already anticipating that their mission may be an anticlimax. Pioneer 11, the dry run for the Voyager missions, had taken the first ever images of Titan, albeit at a considerably lower resolution than Voyager 1 would, and shown it to be a blank, featureless disk. And as Voyager 1 reached the end of its borrowed time mission, it found that Pioneer's images had been, if anything, too optimistic. Titan was a world hidden from the universe, lost behind a shroud of impenetrable haze. So extensive was this haze that it actually led to Titan's demotion. Prior to Voyager's arrival, astronomers had assumed that Titan was the largest moon in the solar system, but it was forced to concede that position to Ganymede after Voyager showed that what they had initially taken for the surface was merely the top of Titan's opaque atmosphere, which led it to appear about 150 kilometers larger than it actually was. Voyager 1 was able to confirm what Pioneer had suggested. Titan's atmosphere was indeed thick, thicker than Earth's in fact, at 1.5 atmospheres. As predicted for a thick atmosphere, nitrogen dominated, at 98.4%, with the notorious methane only making up 1.6% and hydrogen 0.2%. This meant that Titan had the only dense, nitrogen-rich atmosphere in the solar system other than our own. But Voyager 1 did make one truly titillating discovery. The most exotic models were right. Titan did indeed hover at the methane triple point. But the visions of methane storms, rising methane waves, crashing on reefs of ice would have to wait until the arrival of a more capable craft. Needless to say, when that craft arrived, it was primed to, well, attack Titan. Not only did Cassini possess a radar mapping device specifically designed to peer beneath Titan's clouds, but it also carried with it a peculiar bit of cargo courtesy of the European Space Agency, a small probe called Huygens. In the most distant landing ever performed by a spacecraft, Huygens would descend to the surface of Titan, beaming what it saw from its first break through the haze to its final arrival on the moon's icy ground. These probes revealed a world that shocked in its similarity to our own. From its smooth river pebbles and craggy mountains covered in methane snow, To its dry riverbeds resembling nothing so much as arroyos from the American Southwest, Titan appeared as a dark photonegative of Earth, a billion miles from the Sun. And in January 2007, while passing over Titan's North Pole, Cassini's radar mapper confirmed what everyone had hoped. The weird waters of Titan had indeed formed into lakes, a suite of hydrocarbon mirrors scattered across the Titanic Arctic. The largest, the wonderfully named Kraken Mare, has a volume comparable to that of the Caspian Sea, the largest freshwater lake on Earth. The lakes were clearly fed by tributaries, and almost mirror smooth, though the occasional ripple has been detected. But for those who dreamed of methane seas as deep as our own, all hope was shattered. Titan was a desert world. A desert built of solid water, but a desert nonetheless. Ironically, it was too warm for liquid methane to permanently collect in its lower latitudes, which were dominated by huge fields of rolling dunes, not of sand or even of ice, but of solid hydrocarbons. But those dry riverbeds seen by Huygens had to have been filled at one time. Were they a relic from Titan's distant past, like the rivers of Mars, or were they periodically filled with seasonal rain? It's important to note here that seasons on Titan are on a scale unimaginable to any Earthling. Saturn's year is 30 Earth years long, so Titan's seasonal regions might lie fallow for decades. Thankfully, Cassini's 14-year tenure around Saturn amounted to fully half a Saturnian year, and so it was able to observe the seasonal transition as Titan's northern hemisphere passed from winter into spring. As Saturn entered its equinox in 2009, the Cassini team saw the equatorial region erupt in methane clouds. During one such cloud event, the Cassini team observed a dark patch on Titan's surface appear to darken further, indicating that it had been moistened by falling rain, the first ever direct evidence for extraterrestrial rainfall. However, models suggest that rain on Titan would be very different indeed to its equivalent on Earth. The lower gravity and thicker atmosphere mean that not only would rain fall more slowly, but the droplets could grow much larger, twice as large as raindrops on Earth. Titan is the only other world in the solar system on which rainbows might be observed, though you'd probably need night vision goggles to see them, since most of the sunlight penetrating the endless haze is infrared. One pressing question is where the methane in Titan's atmosphere came from in the first place. Over time, the Sun should have converted all the methane into more complex hydrocarbons, so the methane must be replenished from somewhere. The leading place of origin is within Titan itself. Cryovolcanism has yet to be observed on Titan, but many mountains seen by Cassini have craters at their tops, suggesting they may be dormant or inactive volcanoes. Titan also possesses jagged, sharp-edged mountains reminiscent of the Alps or the Rockies. On Earth, these mountain ranges, known as fold mountains, are produced when tectonic plates crash together and crumple upwards, so their presence on Titan implies something similar might be occurring under its surface, albeit of ice and water rather than rock and lava. Between 2005 and 2007, Cassini observed surface features on Titan to shift up to 30 kilometers, suggesting its surface was decoupled from its interior. This likely meant that Titan had an active, quote, mantle of liquid water and ammonia beneath its frozen surface that could serve as a reservoir for any water lava. But therein lies the rub. Rock is denser than lava, so lava can't wait to burst out from under it. Liquid water, however, is denser than ice, meaning that it needs some form of additional energy to erupt through it. Some have claimed that this means cryovolcanism cannot be occurring on Titan. Others argue the additional energy could come from an external source, such as tidal flexing, similar to that occurring on Europa. But if Titan were proved to be a frozen analog of our Earth in every physical respect, is it then possible, as Huygens himself had suggested, that it might possess that one attribute so far unique to Earth? Life? Might some alternate cryonic evolution have produced a psychrophilic organism happily swimming in Titan's frigid methane seas? The idea is not as outlandish as you might think, and believe it or not, we may have found evidence of it already. In 2005, an astrobiologist named Chris McKay proposed a possible mechanism for life to subsist on Titan's surface. Titan's atmosphere contains no free oxygen, which is a very good thing, since if it did, the slightest spark would cause it to react explosively with methane and hydrogen, effectively turning the moon into a giant gas bomb. Most life on Earth requires oxygen to produce energy, though there are many examples of extremophiles, unicellular organisms found in highly atypical environments, that do not. One such example is methanogens. These single-celled organisms respire hydrogen instead of oxygen and produce methane as a byproduct. Free diatomic hydrogen does exist in Titan's atmosphere, and using it, McKay showed, it is possible to create a successful energy-producing reaction with the materials available on Titan. One proposed reaction combined hydrogen with ethane to produce 14 calories of energy per unit of hydrogen consumed. Another combined hydrogen with acetylene to produce 80 calories per unit of hydrogen. It should be noted at this point that the respiration we use produces nearly 700 calories per equivalent unit of oxygen, and without that extra energy, any methanogenic life on Titan is unlikely to be larger than your average stomach bug. But McKay did more than model his alternate life form. He made a prediction about how it might be found. If these creatures existed, then they would be consuming any hydrogen that came their way, and so would manifest as hydrogen levels fell dramatically near the surface. And, in 2010, Daryl Strobel of Johns Hopkins University found just such a pattern in the hydrogen in Titan's atmosphere, though he was quick to say that such results were extremely tentative and could be of non-biotic origin. The discovery of a methanobiotic life form on Titan would be one of the greatest finds in scientific history, greater even than locating life on Europa or Mars. Any life on those worlds, at least as we surmise it, would be comparable to that of our own world, using the same chemistry and existing within similar tolerances for such things as heat, cold, or acidity. Indeed, there is some chance it may even have a common ancestry with terrestrial life, having spread between them on meteorites. But life on Titan, particularly life in Titan's exotic lakes, would be of an entirely different order. Adapted from its molecules up to subsist in an environment so alien that not even our most resilient extremophiles could endure it. To compare such life to our own would be to compare a stonefish to a stone. There is no way that such life could have shared ancestry with ourselves. It would have to have emerged completely independently of life on Earth. That would mean another confirmed example of abiogenesis in our solar system. It would immediately answer one of the standing questions of the Drake equation. How likely is the formation of life on a habitable world? And the answer would be almost inevitable. If life could form twice in our own solar system, and under such vastly different circumstances, then we would be mad to assume that it could not do so everywhere. There is, however, one fundamental problem with the concept of liquid methane-based life, and that problem is water. Despite my having spent the entire first video emphasizing to you just how common and humdrum water is, the simple fact is, water is weird. Like, really weird. Take the fact mentioned above, that liquid water is denser than solid water. Have you ever noticed how strange that is? That ice floats on water? If you drop a lump of solid iron into a vat of liquid iron, it sinks, because solids are denser than liquids. This is true for nearly every substance you can think of, including methane, so if you were hoping for an ice skating trip on Titan, you're out of luck. If water behaved like a normal liquid, then ice would sink to the bottom of rivers, lakes, and ponds, and they would freeze from the bottom up, leaving little room for fish. What magic allows water to somehow levitate on itself? The answer is tied to the one property of water that just might make it uniquely qualified as a solvent for life. Water's primary role in the sustenance of life is as a solvent. It is the medium through which the myriad complex molecules and nanomachines that make up our cells and organs mediate the cascade of evolving interactions that drive our biology. And as solvents go, water takes some beating. In fact, water is sometimes called the only true universal solvent, because it dissolves more substances than any other chemical. Everything from salt and sugar to iron, copper, and zinc. All of these substances, to various degrees, are required for life on Earth to function, and are obtained through their solubility in water. Also, as anyone who has overfilled a kettle knows, water possesses a remarkably high specific heat capacity. It takes a lot of energy to turn it from a liquid to a gas, meaning it stays stable over a broad range of temperatures. This not only grants water-based life a broad range of potential habitats, but gives water a crucial role in moderating Earth's climate, as it acts like a storehouse for heat. All of these oddities can be traced to one specific property of water. It is one of the most polar solvents in existence. What that means is that while a water molecule is chemically neutral overall, the oxygen atom is so hungry for electrons that it steals them from hydrogen atoms, meaning that one side of the molecule is positive and the other side is negative. It thus possesses two poles, like a magnet, and indeed, water is, in a sense, magnetic. If you hold a static electricity source next to a stream of water, the stream will be pulled toward it like iron filings to a magnet. The upshot of this is that the water molecule's famous Mickey Mouse head is in fact a three-legged stool, with a third leg made up of a pair of free electrons. These electrons create what is known as the hydrogen bond. They pull at other substances, breaking them into their component atoms, granting water its unique dissolving ability. They also seek out other water molecules, forming weak bonds with them. These bonds keep water molecules from moving apart, and so demand a great deal of heat before transitioning to a gas. Conversely, they also prevent water molecules from moving closer together. As it cools, water loses energy, and so can no longer overcome the bond, and the molecules remain apart, which is why ice is less dense than water. Even beyond this, there is evidence that water plays an active role in the functioning of life. Proteins, the building blocks of living matter, can assume a virtually infinite variety of forms, but within living things they are confined to those forms beneficial to the organism. These forms are moderated by water. Some parts of a protein are attracted to water, some are repelled, and the presence of water forces proteins to fold in specific required ways. Liquid methane, unfortunately, has none of these advantages. It is not polar, and so cannot dissolve substances like proteins. It is liquid over a range of just 20 degrees Celsius, compared to 100 degrees for water. But perhaps we're being a little too Earth-centric here. Ethane, which is also present on Titan, is liquid over a comparable range to water. Water's voracious solubility also means that it breaks down large organic molecules that would remain stable in a liquid methane medium. Also, some have argued that far from assisting the creation of complex molecules, the power of the hydrogen bond actually disrupts processes like protein folding, meaning that they would be easier in a methane medium. And while proteins cannot dissolve in methane, polylipids can. And as long as 40 years ago, Isaac Asimov suggested that polylipids could form the basis for biology in a non-polar solvent. This does, however, make forming a cell membrane rather difficult, since cell membranes are made of polylipids precisely because they don't dissolve in water. However, in February 2015, astrobiologists constructed a hypothetical cell membrane using a substance called acrylonitrile, which contains carbon, hydrogen, and nitrogen. Called an azotosome, which literally means lifeless body, but in this case is meant to mean nitrogen body, this structure was able to maintain integrity in a liquid methane environment, and could possibly serve as an alternative cell membrane. Finally, there is the simple fact that even if life is impossible on Titan's surface, we know that Titan does possess a liquid water mantle, probably as large as the one suspected under Europa. Titan could still be home to life of the humdrum terrestrial type, perhaps even both. The possibilities hidden in the dizzying, strange beauty of Saturn's largest moon have ignited dreams not felt since the days before the space program, when we imagined beautiful, buxom women on Venus and stern father figures on Mars. The thought of an entirely new form of life hidden just beyond our reach has scientists thrumming with anticipation, and NASA drawing up distant plans. For now, eyes are focused on Europa, but everyone knows where they'll be going next. Join me next time, when I'll be exploring the rest of the Saturnian system, and in particular, one pint-sized hotshot world who rakishly stole the show.